Welcome to CECS 228. Today we're going to be considering Relations Part 1, which deals with the properties and operations of relations. This material is going to seem very familiar because it's actually something we have addressed in basic structures. The first thing that we took a look at in Part 1 of basic structures was sets, and we took a look at the Cartesian product of two sets, which produces ordered pairs. More generally, we could take n distinct sets or n same sets and form the Cartesian product to come with an n-tuple rather than a tuple. Then we later placed restrictions on how we can form those n-tuples. We said, well, if we want to create a function, we need to make sure that every input element from the domain gets assigned to only one output element. And so that gave us a little bit of more structure, and it allowed us to define things such as an onto function and a one-to-one function. But there are many scenarios where we don't want to have just a one output mapped to a single input. Sometimes we have situations in which there are a one-to-many. So in that case, it's necessary to simply consider a relation, or in other words, just the Cartesian product of sets. So in this series of lecture notes, that's what we're going to be focusing on. And if you want to take a look at sections 9.1, 9.2, might be a good reading before you continue to consider the rest of the video. So the first thing that we're going to consider is a binary relation. We're going to let A and B be sets. A binary relation R from the set A to the set B is a subset of the Cartesian product A cross B. So meaning you have tuples where the first element comes from the set A and the second element comes from the set B. If the tuple A comma B is in R, then we might also write it as the first element, the name of the relation, in this case it's R, and then the second element. So for instance, let's say that A is a set of first-year undergraduate students and B is a set of courses, and R is going to define a relation that has ordered pairs A comma B, where A is a first-year CECS student taking a course B. Then we're going to further assume that Calvin is a first-year student who is taking CECS 174. Then we would say that Calvin, CECS 174 is in R, or using the second notation, we would have Calvin R CECS. This should be 174. But Calvin, Math 520 would not be an R because Math 520 is a graduate course, and we're assuming that Calvin is a first-year undergraduate. So this ordered pair would not be part of the relation. All right, let's take a look at example number 2. Example 2 has A being the set of elements 1, 2, 3, 4, and the relation R is defined as a set of ordered pairs A comma B such that B is A times some integer K. So essentially that's just a formal way of saying that B is a multiple of A. So R is a relation from the set A to itself. So we want to take a look at what's going to be part of relation R. So if we think about an input of 1, and we think about what multiples, what numbers in set A are multiples of 1, well, that would be all of them, right? 2 is a multiple of 1, 3 is a multiple of 1, 4 is a multiple of 1. So we are going to find the ordered pairs 1, 2, 1, 3, 1, 4, as well as 1, 1, because 1 is a multiple of itself. Then if we think about the input being a 2, meaning the first coordinate being a 2, and we think about what multiples of 2 exist within the set A, well, that would just be 4. So we would have 2, 4. And then if we think about 3 as an input and look at just be 3 with itself, right? There's no additional multiples. And same thing with 2. Okay. And then if we look at 4, it's the same idea, right? There are no other integers in here that are multiples of 4 other than 4 itself. So we would have 4 comma 4. Now, more generally, an n-ary relation is a relation that's defined over n sets. So we have a1, a2, all the way down to an as sets. An n-ary relation of these sets would be a subset of the Cartesian product of those n sets. And these sets, a1, a2, down through an, are called the domains of the relation, and n is called its degree. Okay. So let's take a look at example number 3. For each of the relations below, give one element that is part of the relation and one that is not. And part A is the relation on n cross n cross n, consisting of triples of integers a, comma b, comma c, with the condition that a has to be strictly less than b and b has to be strictly less than c. So these are the domains is just a set of natural numbers for each of the 3 coordinates. So we can simply take maybe, for instance, 1, comma 2, comma 3, and that would be part of the relation because it satisfies, first of all, that these are natural numbers, and second of all, that the first coordinate is less than the second, and the second is less than the third. Okay, something that would not be part of the relation would be something maybe like, let's say 3, comma 4, comma 2. There are infinitely many that are not part of the relation, but this is just one of them. In this case, it's not a relation because the second coordinate is not less than the third, and that's a requirement that B has to be less than C. Part B reads, let R be the relation on Z cross Z, which is a set of all integers. So these are all triples such that A, B, and C form an arithmetic progression. That is, the triple ABC will be part of the relation if and only if there is an integer k such that B is A plus k and C is A plus 2 times k. So to come up with the triple that is part of the relation, we can simply start by defining what A should be. So for instance, we could let A be 2. And we could also define what K should be. So maybe K will be 3. Then B is going to be, and then I'm going to start forming the triple. A is 2. And then B is going to be 2 plus K, so that would be 5. And then C would be 2 plus 2 times 3, so that would be a 2 plus a 6, which is going to give us an 8. Or more simply, to get the second coordinate, we add 3 to the first coordinate. To get the third coordinate, we add 3 to the second coordinate. Right, so that's the meaning of an arithmetic progression. So that would be something that is part of the relation. Even though they only ask for one triple, I'm going to go ahead and give a couple more just so that we get a feel for what else might be as part of the relation. We could also have, for instance, 0, 0, 0 be part of the relation. And the reason why that would work is because we're simply letting the first coordinate be 0, and then the constant that we're adding every time is just 0. Okay, so 0 plus 0 will give us a 0, and then 0 plus a 2 times 0 will give us a 0. The same can be said about 1, 1, 1, because in this case we're letting A be 0, A be 1, and K be 0. And then the first one will be 1 plus 0, which is going to give us 1, and then, the second one, and then the third one would be a 1 plus 0, which is still going to be 1. So something that would not be part of the relation could be something that could, is something maybe like 2, 4, and then maybe 8 is not part of the relation. Okay. because what we're adding to the first coordinate in order to get the second is a 2, but then in order to get third, we no longer are adding a 2, right? We would be adding a 4. In fact, the way that I kind of came up with this was simply by taking the first, second, and third power of 2, which is not an arithmetic progression. Okay, so that's something that's not part of the relation. Alright, so how do we use these n-array relations? Well, perhaps the most useful application is databases. So we use n-array relations to represent database records in a manner that makes adding, deleting, updating, searching, and combining records efficient. So such a representation is called a relational data model. And in this model, every record is represented by an n-tuple. And every n-tuple, every element of the n-tuple belongs to a field. So for instance, maybe you have, in this case, we have four elements that are part of our n-tuple, and the first coordinate is representing the name of the record. The second is the age, followed by height and weight. Now, some important definitions for that are necessary when talking about databases are primary key and composite key. So we're just, for the purposes of these definitions, going to let R be an n-array relation. That means it's going to consist of n-tuples that have this form, and it's going to be a subset of the Cartesian product of these domains, so A1, A2 down to AN. And what that means is that this first value, x1, has to come from the set A1. x2 will come from A2, so on and so forth. Okay, so based on that assumption, the primary key of R is the domain A sub I for some I in the range 1 through n. So it's one of the A's in this Cartesian product. And it's going to be the one that makes each n-tuple unique, meaning no two n-tuples are going to have the same value for the field xi. Yeah, primary key should always be chosen so that it's time independent. So what that means is that if you have a database where the values might change, so for instance, if we have a database that consists of records of this type, the age of the person will change according to time. Their height and their weight could potentially also change, especially maybe if we have the record of a child, their height will definitely be changing. So you wouldn't want to choose a primary key to be, for instance, the height or the age, because then every time, as time progresses, you're gonna have a changing key, so you're not gonna have the same record returned if you're using the same key. So like say for one record, you decide that the key will be the age, and at the time that you decide that, we have one child whose name, let's just say, is Bob, with, I don't know, we'll say height of 4 feet and a weight of 60 pounds. So let's say that you choose age, you use age for the primary key, and then you make a search where you want you want each record to be identifiable by the age. So you say pick out all the elements that have a key of 8. Okay, well, first of all, that's not going to be unique. If you have a large database, it's likely you're also going to have other children age 8. But second of all, next year, Bob is no longer going to have the same key value. So even if you did have a database with only one child age 8, by the following year, you're not going to be able to access Bob through the same key because he's no longer going to be associated to the number 8. It's going to be 9 now. So you want to make sure that primary keys are chosen so that they're time independent and so that no two n-tuples have the same field or run the risk of adding a new database that will have the same the same field value. So that is primary key. We now take a look at a composite key, which is going to be the Cartesian product of domains of R that uniquely define the n-tuples of the relation. So a composite key can be used in the place of a primary key if the primary key is not possible. Okay, so what this means is maybe you might have a database where no domain will uniquely define the tuple or the record, meaning it's possible that, like in this case, you will eventually have two different records with the same name, and maybe two different records with the same age, two different records with the same height or weight. So none of those individually might be good candidates for being a primary key. In that case, taking two of the domains together could form a composite key. So here's another example. Let's say you have another database that consists of records of the form name. Maybe they have a telephone number that consists of area code for the second coordinate and the actual phone number for the third. Okay, and then maybe followed by the age, and I don't know, we'll just say maybe height. Okay, then we could have the possibility that two different tuples have the same name. We could have the possibility that two different tuples have the same area code. But they're for sure not going to have the same area code and phone number unless maybe you're taking more people from the same household. But let's say that this database contains at most one person from each household, which means that they're going to be at most one record with the same area code and phone number. Then in this case, you might want to create a composite key that takes precisely the cross product of those two domains. Okay, so in this case we would take A2 cross A3, and that would be a form of identifying our n-tuples uniquely. Okay, so let's take those concepts and put them into practice by looking at example 4. It's asking us which domains can be a primary key for the n-ary relationship displayed in Table 1, assuming that no additional records will be added. Okay, so table number 1 has, first of all, 4 fields. We have student name, ID number, major, and GPA. And if you take a look at ID number, those are all unique, right? Every student receives their own identifying number, which is the ID number. For student name, those are all also unique. There are no two students with the same name. The major, they're not unique. We see two different records with the same computer science major, two different records with the same math major, and GPA is also not unique. There are two with 3.45. So when it comes to primary key, we would definitely not use major. We would definitely not use GPA. We could either use the student name or the ID number. Okay, so primary key possibility number 1 could be the ID number. The second possibility could be the student name. Okay. Here's my take on this, however. Even though they do mention that no additional records will be added, let's say that in the future they were to change their minds and they actually add some more records to this table. Then we could potentially end up with a student that has the same name as one of the pre-existing records. So student name would probably not be so desirable if you're going to grow the table in the future. ID number would be the best option for a primary key because every student has a unique ID number. So if you ever have to go and search, you would search by ID number, and it'll give you only one student pertaining that is relevant to that record. So this one, I'll just write careful. This is not appropriate for growing table. Okay, part B. What domains can form a composite key? Well, anything that has student name in conjunction with maybe major or GPA could be a composite key. Anything with ID number could be could form a a composite key. Simply because we've already seen that those already uniquely define an n-tuple. But what if there were some types of repetitions or some repeated values in ID number and student name? What we could do is take the cross product of two domains that uniquely define together the records. So for instance, I see here that computer science with a GPA of 3.88 only exists once, right? The other computer science has a 3.49. With the mathematics, there's one with 3.45 and another one with 3.90. So if we were to take a composite key of major with GPA, that could also uniquely define each record. So that's one possibility, and like I mentioned earlier, student name with anything else would also form a composite key, and ID number with anything else would also form a composite key, because by themselves they already define unique n-tuples. Okay, so we're now going to discuss operations on these databases, starting with the selection operator SC. So SC is going to act on the relation as a whole. So here I'll write R. And the output is going to be also a relation that is a subset of R. I'll call that R prime. Okay, so what it actually does is it returns all the records that meet condition C. So I guess as part of the input, I should also write C here, which is a condition. All right, projection operator P sub I1, I2, all the way down to IM. This one is actually going to act on an individual tuple or n-tuple. And it's going to output an m-tuple. So the way it works is it basically says, okay, we're going to take only the I1, I2 down to IM fields of the n-tuple and return those. So if you have something like x1, x2 down to xn that it's acting on, that is going to return the tuple xi sub 1, xi sub 2, down to xi sub m. And finally, the join operator. The input are two relational databases. So R is going to be, let's say, an n, a relation of degree n. And S is going to be a relation of degree m. Okay, so remember, this means the number of fields. So R is going to have n fields, S is going to have m fields. And the other thing too is that they need to have this, P is going to define how many of the fields should agree. So what needs to be true about this is that the last P fields of R agree with the first P fields of S. Okay, and what does it return? Well, it's also going to return a database, meaning it's also going to return some relation. I'll call it Q. And it's going to have a degree of m plus n minus p. So basically what it's going to do is it's going to merge the records of the two databases. So I'll say merges records shared in common. By R and S. Okay, so let's apply these operations. For example 5, part A, we have what operator would you need to use to find the records of computer science majors in table 1. So table 1 was the table with the different students, majors, GPAs, and ID numbers. And in this case, we're trying to pick out all of the records that have a major of computer science. So, well, it wouldn't be the join operator, and it wouldn't be the projection, it would be the selection operator, where the condition is that the major is computer science. So we would need selection operator as C, where C is the condition that major has to equal computer science. Alright, for part B, what results when the projection operator P1, 3 is applied to the four tuples 2, 3, 0, 4, Jane Doe with what seems to be an ID number, geography, and 3.14, and this general four tuple A1, A2, A3, A4. Okay, so P1, 3 acting on 2, 3, 0, and 4 is simply going to take the value from the first field and return it, as well as the value from the third field and return it. So that would be a 0. We repeat the process with Jane Doe, the ID number, I'm just going to write ... geography, and 3.14. We're going to get Jane Doe for the first field and geography for the third field. And finally, if we applied P13 to this general 4 tuple, we're simply going to get back A1 and A3. For part C, it reads, what relation results when the join operator J2 is used to combine the relation displayed in table 6 and table 5 and 6. So table 5, it's a little difficult to read here, but table 5 is called teaching assignments. Table 6 is called class schedule. And on teaching assignments, we have a domain of professor, department, course number. For class schedule, we have department, course number, room, and time. So as we can see, the 2 here is defining the last 2 fields of the first table and the first 2 fields of the second table that agree. So based on those 2 domains, we need to now merge the relations, or we need to join the relations. So the result is going to be the following. We'll start with the domain. So we're still going to have a professor domain. We're still going to have a department. We're going to have course number. Now we're also going to have room and time. And what we can do is we can start with looking at the first record of the first table, which is Cruz from the zoology department with a course number 335. And then we'll see what matches on the second table. So here it is, zoology 335. That'll be room A100 at 9 a.m. Okay, next one is Cruz, also zoology, room 412. Here it is, 412 is A100 at 8 a.m. Next one is Farber. Farber has psychology 501, and that one also appears here. Okay, and we're going to have A100 at 3 p.m. Okay, next one is Farber with Psychology 617. Okay, and I'm verifying every time to make sure that there is a record on both databases so that I can merge them. Because if they're missing information on one of the 2, then we're not going to add it to this joint database. Okay, so this one was 617, and that would be A110 at 11 a.m. Okay, next one is grammar, physics 544, and that one is found here as well. Okay, and then notice the next one is also grammar of physics, but now it's 551. In the second database, we only have one physics class, and it corresponds with a course number 544. So because we don't have that second record of physics, we're not going to be adding it to the join. Okay, so I'm just going to place a little mark there as a reminder that we didn't add that one. Okay, next one is Rosen with computer science. So let's see, computer science 518, and here it is, computer science 518. And that's going to happen at N521 at 2 p.m. Okay. Now the next one is Rosen with mathematics at 575, so that is here. Okay, and that ends all of the records in the first table. In the second table, we're just going to check if there are any that were left out from the joins database. So computer science with 518 appears here. Math with 575 appears here. Math with 614, however, is not part of our database. And reason being is we didn't have a corresponding record over in table number 5. Then physics with 544 we have here. Psychology with 501 we have here. Psychology with 617 is there. Zoology with 335 and zoology with 412 is here. So the moral of the story is if there are records on one relational database that do not appear in the second relational database, then we keep them out of the joint relational database. The last thing that we're going to discuss in this video is properties of relations. So here are the 5 properties that we're going to be considering, and we are thinking about a relation R defined over a domain A. So we say that R is reflexive if for every element in the domain, A comma A is part of the relation. It'll be symmetric if whenever A comma B is part of the relation, then B comma A is also part of the relation. So basically, if you have an element, let's say 1 comma 2 as part of it, then 2 comma 1 will also be part of the relation. Okay, it's going to be anti-symmetric if whenever A is in A comma B is in R and A comma B is in R, that means that A has to be equal to B. So in other words, the only elements for which this is true is for elements that look like the same first coordinate and the same second coordinate. Other than that, we don't have any elements that satisfy this condition, that if A comma B is in the set, then B comma A is also part of the relation. Asymmetric is similar to anti-symmetric, except that it doesn't even allow for tuples where the first coordinate and second coordinate are the same. So it's asymmetric whenever A comma B is in the relation, then that means that B comma A is not part of the relation. And finally, it's transitive if whenever A comma B is part of the relation and B comma C is part of the relation, then that means that A comma C will be part of the relation. So we're going to exemplify all of those properties by considering the following example. So here we're given 6 different relations over the set 1, 2, 3, 4. And if you look at page 6, part A, they're asking us which of these are reflexive. And I've rewritten the definition of reflexive here at the top. It means that for every element in the domain, A comma A has to be part of the relation. And in this case, the domain is these four integers. So if you look closely, R1 would not be reflexive because it does have 1 comma 1, 2 comma 2, 4 comma 4, but it's missing the 3 comma 3 that is necessary to the definition of reflexive. So R1 would not qualify. Then for R2, it only has one of the 4 required ordered pairs. It only has the 1 comma 1. It's missing the 2 comma 2, 3 comma 3, and 4 comma 4. From there, R3 does contain all 4 elements, 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4, so that one would be reflexive. R4 doesn't contain any of the elements. It doesn't have 1, 1, 2, 2, any of those. So for every element in the domain, A comma A is not part of R4. R5 is reflexive. Again, it contains 1, 1, 2, 2, 3, 3, 4, 4. And finally, R6 doesn't contain any of the required elements, so that one is not reflexive. Okay, so the only reflexive relations would be R3 and R5. Okay, the next one is symmetric. Which one of these are symmetric? And again, I've rewritten the definition here a little bit different to how it appears in page number 5, but it's just so that it's a little bit clearer. So it'll be symmetric if for every element of the form A comma B in the relation, then B comma A will also be part of the relation. And again, I'll try to fit the relations as much as possible. So if we look at the first relation 1 comma 1, it has this element 3 comma 4, but 4 comma 3 is not part of the relation, so that means that it's not symmetric. If we look at R2, we have 1 comma 1, which if you switch the order of the coordinates still gives you the same element. Then we have 1 comma 2, and if we switch the order there, we would have a 2 comma 1, and that is part of R2, so R2 is symmetric. If we go to R3, we would have 1 comma 1, which switch gives you the same thing. Then 1 comma 2 requires that 2 comma 1 be part of the relation, and that's here. 1 comma 4 requires that 4 comma 1 is part of the relation, and that's here. 2 comma 2 is there, 3 comma 3, 4 comma 4. Those also, if we switch the order again, we get the same element back. So that is symmetric. And that's our next symmetric relation. Then for R4, we have 2 comma 1, which would require a 1 comma 2, but that is not part of the relation. So that one is not symmetric. For R5, we have a 1 comma 1, that's fine. 1 comma 2 requires a 2 comma 1, but that is also not part of the relation, so that is not symmetric. And finally, for R6, we have a 3 comma 4, which would require a 4 comma 3, and that's not part of the relation, so R6 is not symmetric. Okay, the next one is antisymmetric. Let me just go ahead and highlight our correct answers here. The next one is antisymmetric, and antisymmetric says that if A comma B is part of the relation and B comma A is part of the relation, then that means that B has to be equal to A. In other words, it doesn't allow for the symmetry to happen, but it does allow for ordered pairs where the first and second coordinate are the same. So again, if we look here, we have 1 comma 1, which is fine. Then we have 1 comma 2, so we need to make sure that 2 comma 1 is not part of the relation, but it is. So because it's there, that won't be antisymmetric. The same will be true about R2, and the same will be true about R3. R5 and R6 are the only ones besides R4 that satisfy. So if we take a look at R4, 2 comma 1 means we have to make sure 1 2 is not there, and it's not. 3 comma 1 requires that we don't have 1 3, and that's not there. 3 2 means no 2 3, looks good. 4 1 means a no to 1 4. 4 2 means a no to 2 4, and finally 4 3 means a no to 3 4. So that looks good. Then for R5, we have 1 comma 1, which is fine. Then 1 comma 2, we need to make sure that 2 comma 1 is not there, looks good. 1 comma 3 means 3 1 shouldn't be there, okay, good. 1 comma 4 means 4 1 shouldn't be there. 2 2 we said should be fine. 2 comma 3 means 3 2 should not be there. 2 comma 4 means 4 2 shouldn't be there. And 3 3 is fine. 3 4 means 4 3 shouldn't be there, and 4 4 is good. So R5 is good. And finally, R6. R6 is simply 3 comma 4, which means we need to make sure that 4 comma 3 is not part of the set, and it's not. So, so R6 would be considered antisymmetric. Okay, part D, we have asymmetric. Now for asymmetric, the definition is that if A comma B is an R, then B comma A cannot be an R either, and this excludes points in which we have the same first coordinate and second coordinate. So that means that A comma A cannot be part of R. Okay, so if we look at R1, 1 comma 1 is part of it. R2 is the same thing. R3 is the same thing. So these are not going to be asymmetric for the same reason as that they are not anti-symmetric, right? Because they either have a 1, 1 or 2, 2, 3, 3, but they also have these here. They have 1, 2, and then 2, 1. They have these symmetric elements. So that is not, that does not allow for it to be asymmetric. And then if we look at R5, R5 does not have any symmetric elements that with distinct coordinates. So like if I take a look at 1, 2, I'm not going to find 2, 1, but it does violate the requirement that not even the ordered pairs with the same first coordinate and second coordinate should be present. It contains 1, 1, 2, 2, 3, 3, and 4, 4. So that is the reason why R5 is not asymmetric. R4 and R6 are the only asymmetric relations, and we can check. Okay, so here's R4. That means that we have a 2, 1 and shouldn't have a 1, 2. So basically anything that is anti-symmetric and that does not have any elements of the form A comma A will be will be asymmetric. So the ones that were anti-symmetric were R4, R5, and R6, and out of those, R5 did not qualify because it contained the elements of this form. Okay, so the reason why these are asymmetric are the same reasons why they are anti-symmetric, and you can go in and verify and just make sure that there are no symmetric elements in these relations. Okay, finally, transitive. Transitive means that if A comma B is in R and B comma C is in R, then A comma C has to be in R. Okay. And so I'm not going to be checking, I'm not going to show how to check all of these R4, R5, and R6 for transitivity, but I will show you why R1, R2, and R3 are not transitive, and then this is something that you can verify on your own. So R1 is not transitive because 4, 1 and 1, 2 are part of R1. So again, here's R1. But if you take a look, that means that there should be an ordered pair that maps 4 to 2. Okay, and 4 to 2 is not found in R1. So that makes it not transitive. Then for R2, which is this next relation, we have a element 2, 1 and 1, 2. So that means that I should have an element 2 mapping to 2. But that is not true about R2, so that means that this is not transitive. Okay, next one, R3. Okay, so for R3 we have this element 4, 1 and this element 1, 2, which means there should be an ordered pair from 4 to 2. But 4, 2 is not part of R3. And this is a typo. So that means that it is not transitive. So for R4, R4, R5, and R6, what you would need to do is you would need to, you can create, one way to check is to create a map. So I'll just do it quickly here with R4. And take a look at the mapping. Okay, so if I take a look at R4, we have elements 1, 2, 3, and 4, 1, 2, 3, and 4, and 1, 2, 3, and 4. Then 1 gets mapped to a 2. Excuse me. not for R4, it's just 2 gets mapped to a 1, and then a 3 gets mapped to a 1, a 3 gets mapped to 2, a 4 gets mapped to 1, so that's up here as well, and a 4 gets mapped to 2, and a 4 gets mapped to 3. So then we go to the second column, repeat the same process. So 1 doesn't get mapped to anything, 2 gets mapped to 1, 3 gets mapped to 1, 3 gets mapped to 2, 4 gets mapped to 1, and 4 gets mapped to 2, 4 gets mapped to 3. Okay, so then we take a look at the first mapping. 2 gets mapped to 1, but 1 doesn't get mapped to anything, so it doesn't make a connection to a second mapping. Then 3 gets mapped to 1, which again kind of dies there. 3 gets mapped to 2, and then 2 gets mapped to 1. So that means that I should have a mapping 3, 1, because the element 3, 2 is part of the relation, and 2, 1 is part of the relation. And if we take a look, 3, 1 is a valid mapping, right? It is an element that is part of the relation, so that is a check. Then we move on to the next one. 4 gets mapped to 2, and 2 gets mapped to 1. So that means that if 4 gets mapped to 2 and 2 gets mapped to 1, that we should have a mapping 4 to 1. And if we take a look here again, there is a 4 mapping to a 1, so that's a check. All right, then next one, 4 gets mapped to 3. Okay, 4 gets mapped to 3. 3 gets mapped to both a 1 and a 2. So 3 gets mapped to a 1, which means that we should have a 4, 1. And we also have that 3 gets mapped to 2. So that means that we should have a 4 mapped to a 2. So this one we've already checked. It's part of the relation, 4, 1. Now we need to make sure that 4 also gets mapped to 2. And here it is. We have that mapping. 4 gets mapped to 2. So that's also good. And at that point, we've checked pretty much all of the possible jumps that we could have between two pairs of elements, and that means that this is transitive. So you can use that same type of procedure to check R5 and R6. Make sure that for any two elements that are part of the set, if the first ordered pair has the same last coordinate as the first coordinate of the second pair, that there must exist an ordered pair that pretty much combines the two, right? Takes the first coordinate from the first pair and the second coordinate from the second pair. If you cannot find that ordered pair as part of the relation, then that means it won't be transitive. But in this case, you will see that it satisfies for R5 and R6.